Oh, welcome, my friends! In this video, we will introduce the chi-square distribution and discuss the chi-square test of independence and how the test can be completed using the TI-84 calculator. We will discuss the by-hand procedure, but as the test is calculation intensive, we will be using the calculator functions to do most of the work. First, let's talk about the chi-square distribution. Chi is a Greek letter, which looks an awful lot like the letter X, but is shaped slightly differently if you look closely. Like the z and t distributions, the chi-square distribution is a continuous probability distribution used in many hypothesis tests. The distribution only takes on positive values as it consists of squared numbers. The distribution is right-skewed, as can be seen from the graph. This contrasts the chi-square distribution from the z and t distributions, which are both symmetric. Like the student's t distribution, the shape of the chi-square distribution depends on the degrees of freedom. We will talk about how to calculate the degrees of freedom when we look at an example. Also, like the student's t distribution, as the degrees of freedom increase, the chi-square distribution starts to look more like a normal distribution. All hypothesis tests performed with the chi-square distribution are right-tailed tests, so no more worrying about if the test is left-tailed, right-tailed, or two-tailed. Hooray! The purpose of the chi-square test of independence is to determine if two variables are independent of each other. By independent, I mean that the occurrence of the first event has no impact on the probability that the second event occurs, and vice versa. This is the same type of independence that you might be familiar with from your experience with probability, but now, instead of discussing just two events, we are interested in two variables that can each take on multiple levels. For example, we might be interested to know if age and movie genre preferences are independent. The levels of movie preference might be comedy, action, drama, romance, etc., and the levels of age might be segmented as 20 or younger, 21 to 35, 36 to 50, 51 to 65, and over 65. If movie preference and age are independent, people of all ages prefer the movie genre choices in about the same frequencies. If movie preference and age are not independent, a person's age tells you some information about what movie genre the individual is most likely to enjoy. Notice how the variables can be either categorical, like movie genre preference, or numerical, like age, although with numerical variables, we have to decide how many levels that we want to have, and exactly where the cutoff between the levels will fall, which can be difficult to decide. This segmenting essentially transforms the numerical variable into a categorical variable. The data for a chi-square test of independence will typically be given in what is called a contingency table, which you might be familiar with from your experience with probability. The rows represent the levels of one variable, in this case movie preference, and the columns represent the levels of the second variable, in this case age. The inside of the table lists the number of individuals who have characteristics associated with the intersection of the row and column label, such as age 20 or below and have a favorite movie genre of comedy, to which there are 60 individuals in the sample, or between 21 and 35 years of age and have a favorite movie genre of action, to which there are 80 individuals, etc. The row totals tell us how many people in the study fall into each of the row levels, so how many people prefer comedy movies, how many prefer action, etc. And the column totals tell us how many people in the study fall into each of the column levels, such as how many individuals are aged 20 and below, between 21 and 35, etc. And then the grand total is the total number of people surveyed. For a chi-square test of independence, the null hypothesis is always that the row variable is independent of the column variable, and the alternative hypothesis is always that the row variable is not independent of the column variable. And yes, we literally write out a sentence for the null and alternative hypotheses, which might seem a bit odd if you are used to hypothesis tests with means or proportions, where we use parameters like mu or p, and then we had to think about which inequality signs to use. For a chi-square test of independence, we don't have to worry about those things. The null and alternative hypotheses always take on this form. So in our example, the null hypothesis is that movie preference and age are independent, and the alternative hypothesis is that movie preference and age are not independent. Okay, now let's look at the assumptions needed in order to complete the chi-square test of independence. There must be two categorical variables, each with at least two levels. As I said earlier, Numerical variables are okay as well, but they will have to be segmented somehow to essentially turn them into categorical variables. Secondly, randomization must be used to gather the data. Finally, in order to complete the test, the expected counts in each cell of the contingency table must be at least 5. We will talk about what that means when we get into an actual example, which we will turn to now. The following table shows the results of a survey where 1,000 randomly selected individuals were asked if they liked pineapple on pizza. Does the data suggest that generation and preference for pineapple on pizza are independent? Use a 0.05 level of significance. As we can see from the contingency table, individuals surveyed were either millennials or baby boomers. Those are the two generation options, and the responses are either dislike, neutral, or like with respect to the question. We will go through the same 5 hypothesis testing steps that we always do, starting with step 1, assumptions. Are there 2 categorical variables, each with at least 2 levels? Yes, the 2 variables are generation, with levels millennial and baby boomers, and preference for pineapple on pizza, with 3 levels, dislike, neutral, or like. Was randomization used to gather the data? Yes, the problem states that a random sample was taken. Are the expected cell counts all at least 5? Okay, we still haven't discussed what expected cell counts are, and I promise we'll get to them soon, but we won't be able to verify this assumption until we are part of the way through the test, so we will come back to this later. Step 2, the null and alternative hypotheses. The null hypothesis is that generation and preference for pineapple on pizza are independent, and the alternative hypothesis is that generation and preference for pineapple on pizza are not independent. The null hypothesis of independence would mean that both baby boomers and millennials have the same preferences toward pineapple on pizza. And the alternative hypothesis of no independence or dependence means that the 2 generations have different preferences towards pineapple on pizza. Now, I should mention that when we use the word generation in our hypotheses here, we really are only considering the generations of millennials and baby boomers. There are other generations, like Generation X or Generation Z, which weren't included in this survey, so just know that when I say generation, I just mean the 2 generations that we surveyed. Step 3. Calculations, including the test statistic and p-value. Here's where we get to use the calculator. On a TI-84 calculator, press the second key, and then press matrix, which is under the x to the negative first power button. With matrix A selected, scroll right to the edit menu and press enter. Now you need to change the matrix so that it has the same number of rows and columns as the contingency table, not including the total columns. Our table has 2 rows, millennials and baby boomers, and 3 columns, dislike, neutral, and like. So we can press 2, enter, 3, enter to change the matrix to a 2x3 matrix. Now enter the values inside the contingency table, again remembering that we don't need to enter the totals. So we have 360, enter, 150, enter, 90, enter, 260, enter, 100, enter, 40, enter. Now press Stat and arrow to the right twice to get to the tests. Press the up arrow to get to the bottom of the list. You will see option C, which is the chi-square test, which is the one we need. Make sure not to choose the chi-square GOF test. You should never have to change this menu, assuming that you put the data into matrix A. Matrix B is where the expected counts we mentioned earlier will be outputted. Scroll down and press enter over calculate. You should now have the chi-square test statistic, the p-value, and the degrees of freedom. Write those 3 numbers down, and we'll come back to them later. Press second, matrix, and then option 2 for matrix B. Press enter, and we will see the expected counts that your calculator just calculated for you. These are the values earlier that we said had to all be at least 5 as part of our assumptions, so we have verified that final assumption, since all 6 of these numbers are much larger than 5. This is the expected matrix, and can be thought of as what your contingency table would look like if the 2 variables were completely independent. So we can do a little bit of comparing here. There were 360 millennials who disliked pineapple on pizza in our survey. If generation and pineapple on pizza preference were independent, we should expect to see about 372 out of a sample of 1,000 in this cell, so we really aren't too far off. This one happens to be exactly on. If the two variables were independent, there should be 150 millennials neutral to pineapple on pizza, which is exactly what we see in our data. If you want to know how the calculator gets these numbers, it uses this formula. Expected frequency equals row total times column total divided by sample size. For example, for millennials who dislike pineapple on pizza, we take 600 times 620 divided by 1000, which is equal to 372, which is the same number that we got on the calculator. So some of the expected numbers are a little bit different than what we observed in our data, and some are exactly what we should expect. The question is there enough of a difference for us to conclude that the two variables are in fact not independent? To answer that question, we look at the other information that we wrote down earlier from the output. On the graph, we have the chi-square test statistic, which is 5.58, and the p-value is in the right tail of 0.0613. The chi-square test of independence is always a right-tailed test, so the p-value is in the right tail of the distribution. Now, if you wanted to get the chi-square test statistic of 5.58 by hand, you would need to use this formula. The sum of observed minus expected squared divided by expected. So for each of the 6 cells in our table, we would need to take the observed value from our data, subtract the expected value, which we had in matrix B from our calculator, square it, and then divide by the expected value. Do this 6 times for the 6 numbers inside of the table, and then add them all together. It's a bit tedious, which is why we aren't doing it here. If you did that process, you should get 5.58 for the chi-square test statistic. The degrees of freedom are a little bit easier to calculate. They are just r minus 1 times c minus 1, where r is the number of rows in the table and c is the number of columns in the table, not including the total rows and columns. For us, there were 2 rows and 3 columns. So 2 minus 1 times 3 minus 1 is 1 times 2, which is 2. That's how the calculator got the 2 degrees of freedom. Using the chi-square test statistic and the degrees of freedom, you can use the calculator to get the p-value by going to second, distribution, scroll down to option 8 for the chi-squared CDF. The lower bound is the lower part of the shaded region on our graph, which is 5.58, and the upper bound is infinity, but 1000 is plenty large enough. The degrees of freedom are 2. When we press paste, if you have a TI-83 calculator, make sure to match this output. Chi-square CDF, 5.58, comma, 1000, comma, 2. When we press enter, we get 0.0614, which is approximately the same answer that our calculator gave us when we used the chi-square test function. Now we are on step 4, decision. We use the same decision rule that we have for all hypothesis tests. If the p-value is less than or equal to the level of significance alpha, then we reject the null hypothesis. And if the p-value is greater than the level of significance, we fail to reject the null hypothesis. Like I always say, if the p-value is low, the null has to go, and if the p-value is high, the null will fly. In our case, the level of significance is 0.05, and the 0.0613 p-value is greater than the 0.05 level of significance. The p-value is greater than the level of significance, so we fail to reject the null hypothesis. The p-value is high, so the null will fly. Step 5, conclusion. At the 5% level of significance, there is not enough evidence to suggest that generation and preference for pineapple on pizza are not independent. Or if you like, you could replace not independent with dependent. And we are done. Alright, my friends, that wraps up our discussion of the chi-square test of independence. We will be exploring many more fun and exciting statistical topics that you won't want to miss, so make sure to check out our other videos.